this would be as horrible, no, actually 2 or 3 times as horrible as examples 8 and 9 that we did previously. If you could just kind of imagine this, we've got the natural log function composed with this hideous expression where there's a product in the numerator, and we've got basically the natural log of a quotient. The chain rule would come into play for the derivative of the cube root of x squared plus 5, also for tangent cubed x. So we'd have the chain rule, and inside of that we would have the quotient rule, and inside of that we'd have the product rule in the numerator and the chain rule in the denominator, and inside of the product rule we would have the chain rule. So it's like several degrees of what was the movie? Inception? Yes. It's like, oh gosh. Anyway, it's way better than that. We exploit the properties of the logarithm to make the expression that we have to differentiate as simple as possible. And then it's much easier than that. So no derivatives. Natural log of a quotient equals the difference of the logs. So y equals the natural log of x to the 5th times x squared plus 5 to the 1/3 minus the natural log of tangent x cubed. So, no derivatives, just log of a quotient equals the difference of the logs. And then we have the log of a product. So we say log of the product equals the, not x, equals the sum of the logs, the natural log of x to the 5th plus the natural log of x squared plus 5 to the 1/3. And we could go ahead and do this here. Natural log of the expression raised to a power. What happens to the power? It goes in front, so 3 natural log of tangent x, like that. And then also the 5 comes out in front, so y equals 5 times the natural log of x plus 1/3 times the natural log of x squared plus 5 minus 3 times the natural log of the tangent of x. At that point, we can think about taking a derivative, because it still involves the chain rule. The log is composed with another function in each case, but there's no quotient rule, there's no product rule, and there's no rule inside of a rule inside of a rule. So dy dx time, there we go, dy dx. This is just the constant multiple rule. Derivative of 5 times natural log of x is 5 times the derivative of the natural log of x, so 5 times 1 over x. Nothing fancy going on there at all. A little fancy for the next one. It's 1/3 times derivative of natural log of an expression is 1 over that expression. Maybe I shouldn't make the division bar that long. 1 over that expression times the derivative of that expression minus 3 times derivative of the natural log of an expression is 1 over that expression, 1 over tangent x times the derivative of tangent x. The remaining derivatives, I think, goodness, I might need a little bit more space, but nothing really difficult left. 5 over x plus, could we say 2x over 3 times the quantity x squared plus 5? You know, the derivative of x squared plus 5 is 2x. And then minus 3. I really would like the 3 to be a factor of the numerator. 3 times something with tangent x in the denominator. What's the derivative of tangent x? Secant squared x. And there are certainly alternate ways to write secant squared x over tangent x. I don't know if there's one that's obviously better, shorter, sweeter, clearer than secant squared x over tangent x. You might have a nice...
It's supposed to be another parentheses down on the bottom there. 3x squared plus
2x over 3x.
So, to see what... Oh, was it? There it is. Give it a minute, and then one more minute to see what we... what else? I guess I need to take stock. I'll go ahead and upload this.